So now you're going to see exercises as well. What I would like to anticipate is that Ramon not only prepared an exercise, but he really did a real monitoring of the city of Riga for 3 years with 130 Sentinel images. And so he did a very interesting analysis of the city. You will see areas which are apparently going down or up. And so it's very interesting also from a practical point of view. And if some of you are working structural engineering or in the municipality and so on, you can share, or you should share these results with your colleagues, and then of course study them for real interpretation.
Yeah. Thank you, Francesco. Yeah, Francesco advised me to already show you what it looks like, so that you know, we're going through all the equations, and maybe if you are not interested anymore, maybe then you can see what you're going to get. So this is the portal that we made. So this is data over Riga. And basically what you can see if you go down and you zoom in are the data for single scatterers here, right? And see how they behave over time. And so what I prepared, what we're going to look at in a minute, is an let me see, a website, and it's this website. So it is called sites google.com view isa-riga. And if you get there, there will be the login codes and so to get into that portal. But I think we can do that in a minute. I first would like to finish, let's say, this first most important theory part. Is that okay? But then at least you know what is coming up, right? So later on, before the lunchtime, I already would like to have a look at that, and then we can have discussions in the afternoon. Okay? So let me see. This is where I was. Okay. So before the coffee break, we were talking about the sensitivity to elevation, right? So having a baseline in the geometry, making the system sensitive to elevation, but we also already indicated that this is actually not so very sensitive. So we're at the meter level or maybe sub-meter level. Get this away here. But the most interesting thing is in deformations. So basically, now that's why I would like to focus on deformation right now. So we have a pixel at time t1 when the satellite acquires an image. Then 6 days, 12 days later, the satellite passes again. It will see the same pixel, but the pixel has moved, right? So how well can we measure that, and how come that we get this very high precision level? Now, maybe a couple of pictures of deformation first. These are actually quite old slides, but they're still relevant. So this is the image of an earthquake in Turkey. And again, you see these whole cycles, and now these cycles should be interpreted completely different to what we did before, right? So before the coffee break, we said, okay, there's a height ambiguity, and from one cycle to the other is maybe 100-meter difference, so this is a mountain, right, or a valley. In this case, it's not a mountain or a valley, but it's deformation. And every cycle here corresponds with 28 millimeters of displacement. So if I have a red point over here, and so this point on Earth, there I go again. How do I fix that?
View full screen.
This one, view. Full screen. Great, thanks a lot. So this point over here and this point over here now are different in the sense that they moved relative to each other. So this red point moved 2.8 centimeters relative to this point. Or if I count the fringes, and I go from here from very close to the fault where the earthquake happened, then this point moved 1, 2, 3, 4, I think it's 26 fringes up to here. So 26 times, say, 3 centimeters, so 75 centimeters of motion of this point here to the Black Sea relative to the fault. So due to the earthquake, actually there was more like 2.5 meters of motion over here relative to the up and down. So totally different interpretation. Other example here, this is a volcano, Mauna Loa on Hawaii. And again here, all these images that you see, the fringes that you see, are now not related to the mountain itself, to the volcano, but they are related to inflation or deflation of the volcano. And finally, an example with subsidence. This is water extraction in Las Vegas. And also here, this little pattern over here. Now, this doesn't indicate topography, but it is deformation. Okay, so now, how do we get there, and what are the equations? And I can promise you the equation will be much easier than what I did before. So the hard part is already over, because this is actually a very easy relationship. The analogy is the same. So I have a satellite at T1 in space. I have a pixel on the ground over here. There's a distance between that is called R1. We have to go twice, two times R1. We measure it with a wavelength precision. So the relationship is the same like we had over here, right? So if we describe it like this, so the observation of one image is psi1, it's related to R1. But that observation is very difficult, well, actually impossible to use unless we difference it with another acquisition. Okay, what happens now is that there is subsidence. So this point now goes down, satellite flies on, but there is delta Z subsidence, maybe 1 centimeter of subsidence. Now the satellite is coming again, and now we assume that the satellite is in exactly the same position. Why do we do that? Well, because then the baseline is 0, and then we will not be sensitive to topography. That's what I before the break, I said if the baseline is not 0, then I'm sensitive to topography. If the baseline is 0, I'm not sensitive to topography. So this is great. If the satellite is exactly at the same position, the orbits are the same, I will have only sensitivity to deformation. I'll get back to that hypothesis in a minute. So what happens now is, okay, so if the satellite is at the same position, the distance now has increased a little bit because of the subsidence, and the amount of increase is this delta P, and we call that the line of sight deformation. The line of sight is the line in which the radar looks, and a radar measures distance, so it can only measure deformation in this direction. It cannot measure any kind of deformation in a plane orthogonal to that line of sight. So if this is the delta Z, then we're only, so if the delta Z is 1 centimeter, we're only going to measure maybe 0.8 of centimeter of that in the direction of the satellite. But 0.8 is measurable. Okay. So the second observation, I have the same distance, similar like I showed you before. And now the difference between the distance R2 is that it is the same as R1 plus this little piece of the displacement. And I can now subtract the two from each other. So the two observations subtracted from each other are the two left-hand sides subtracted from each other. So the R1 drops out, the R1 and the dP. So what remains is the displacement component. So this is the important equation. And the nice thing is that this is very easy, right? Because 4 pi is just a number. You can use it in your calculator. Lambda, we know that, 5.6 centimeters, or 0.056 meters, of course. We're working in meters. This is what we measure. So if we measure, let's say, an angle of 90 degrees, or of half pi radian, I can immediately see how much displacement that is. Okay, so that's the sensitivity. Oh yeah, what is also interesting to see here is that basically if you look at this, so this is, if I can write that down here, so this is the same as minus 2 pi times dP divided by lambda divided by 2. Right? This is the same equation. The 4 pi goes down over here. So this thing here is half of the physical wavelength. So if the physical wavelength of the radar instrument is 5.6 centimeters, then one cycle, one fringe, is half of that. So that is 2.8 centimeters. So one full cycle is 2.8 centimeters. Okay, so now I just had during the break an interesting question about the precision level, and we'll look into that in a minute, but the question is how well can you measure an angle, right? An angle is 360 degrees. Well, by eye, I can already measure an angle of maybe 5 degrees easily, right? So if I did that experiment once with a class like you, and I I said, okay, let's have an angle here. And I asked you, okay, is it more than 30 degrees or less? Is it more than 40 degrees or less? And actually, by averaging all your opinions, I got to a standard deviation of about 3 degrees, right? So basically, by just using your eyes, we can measure an angle easily to maybe like, let's say 6 degrees, right? Now, full angle is 360 degrees. So 1/6 of that is 60 degrees. So 1/60th of that is 6 degrees, right? So if one cycle is half the physical wavelength, so lambda divided by 2 is 28 millimeters, then 1/10 of that would be 2.8 millimeters. 1/100th would be 0.28 millimeters. So 1/60th would be maybe 0.3 or 0.4 millimeters. Right? So the key message is that if we're doing this, if we're measuring the phase difference with interferometry, in principle we can measure sub-millimeter deformation. Right? And that is the crazy thing, right? So we have a sensor which is 800 kilometers in the sky, but if something here on the ground moves with half a millimeter, that is, less than several pages of A4 paper, we're sensitive to this. And so the key thing is this interferometry part. So if you look at an example here, another earthquake, so we can measure the precision in deformation here very, very precisely. There are other error sources, I will talk about that later, but in principle the measurement is sub-millimeter. Okay. Oh yeah, this is what I wanted to show you. So this is as an example. So if this is the the full two-dimensional pattern, we could look at, let's say, one cycle over here. That is what I do by simply blocking out just let's take one little strip so that we can still see something. So this is now one fringe, 2 radians. So here we get the fringes are getting closer to each other. So the 28 millimeters of displacement are getting closer to each other, so there's more deformation over here. Okay, so the phase that we're measuring was 4 pi divided by lambda times the displacement. And this is what I just said, so this is related to half of the physical wavelength. Same thing for 2 pi. So if we have one fringe, one cycle from blue to blue, then the number that we get for 5 pi is 2 pi. So this is one cycle. So then we get 2 pi is minus 2 pi divided by this. And then these 2 pi's drop out. So the displacement for one fringe is half a cycle. That's how we get there. Okay. This is the main message. One cycle is half the physical wavelength. And I will repeat that over the afternoon, and you will see it often. So remember this. One cycle of phase is equal to half the physical wavelength. Now, to finish this off, I was talking before the coffee break about the elevation dependency. So here we have phase, which is related to elevation, to the height of the mountain. And now I've been talking about the sensitivity of the phase to displacement. Now, what's the difference between these two? Well, the lambda divided by 4 pi is in both, but this r1 sine theta divided by the perpendicular baseline, that is only here for the elevation. So in other words, for the topography, measuring elevation, I'm always sensitive to this perpendicular baseline, but for the displacement, I'm not. Right? So this whole sensitivity scaling comes from that, drops out. Now, I also indicated during my explanation that I just assumed that the satellite would be exactly at the same spot. Now, obviously, in practice, that's not the case, right? They are steering the satellite to be almost at the same spot, but it will never be the same the case. So there is always a certain baseline. So basically, the problem that I have is that I have the summation of those two equations. I have one observation, one color in my interferogram, but the problem is I have two unknowns. the displacement, and the elevation. And that's a problem, right? If I have one observation, two unknowns, I cannot solve that, right? If I say A plus B is 7, I will never be able to know what A plus B is. There are many different combinations which will give me the number 7. So how do we solve that? Well, there are many different pragmatic ways. So one very pragmatic way is simply use an elevation model. If you already know the elevation of Latvia, you know for every point what the elevation is. You just put that number here and you get rid of this whole term and you get the displacement which is left. And that is basically in the portal that I showed you, this portal that we're going to have a look at here. This is what we did. So we used the topography, in this case from the SRTM mission, so the Shuttle Radar Topographic Mission, and we used that to compute the elevation for each point in this data set. And that way we can simply ignore that because we remove the topography and we only get displacement left. Okay. The other thing to remember is now the sensitivity for deformation is about 1,000 times higher for deformation than for topography. So deformation, the sigma of less than a millimeter, deformation in the order of a meter or so. Okay, that's it. Questions about this so far? Yeah.
You mentioned just right now you used SRTM. So what is the difference of what, how old or how new is the information about topography? And what's the resolution, for example, as well that you use for that application?
Yeah. That's a good question. So maybe if I want to answer that question, I should go back to actually the homework that I gave you before we went for the coffee break. That was this one, right? And I propose to answer this, that we do this together. Did anybody do this? No? Come on, guys. Hey. All right. Let's do it together, just to see how this goes. Okay, so what did we say? We had this equation over here. Just going to grab it here. Oh. Okay, so this is the equation, right? So let's do this. So let's say that the distance from the satellite to the ground, the satellite Sentinel is about 700 kilometers, I guess, but it's looking to the side, so I just have the value of 1,000 kilometers here. So 1,000 kilometers is 1 million meters. So we had the phi, which was 35 degrees, but that's too difficult for me, so I make 30 degrees, and so the sine of 30 degrees is half square root of 3, right? Then lambda is 0.056 meters. Okay, so I'll make that 0.06 easier. And here we had 2, and this was what we said, I think, did we say 100 meters? I think 100 meters. Right, so if we do this now, so we have 1e6 half times square root of 3. Does anybody 0.7, something like that? Could somebody check that? Maybe, I don't know it by heart. Times 0.7, so that is 7 e to the minus 1 times 6 e to the minus 2 divided by 200. Right, so that is I need to do this by heart. So 7 times 6 is 42 e to the power of let's do it differently. Get confused there. Somebody can do it on a on a calculator. Divided by 200 in any case. So we have 1 million times, what did we say, 0.7, so that is 700,000 times 0.06. This times 6 is 42,000, divided by 200, 0, 0 is off. So that is 210. Right? Maybe if somebody has a calculator, you can try it, but this is, I think, the ballpark number, right? So what did we now compute? We computed the height ambiguity, right? So 2 pi cycles corresponds with 210 meters. Now your question was, how well, should be the precision of the DM, or maybe the DM changes, maybe something changes. Huh? So okay, let's first look at the changes of the DM. So if the ground moves, we're talking about millimeters per year, right? Or maybe a centimeter per year, but not meters per year, right? That would be dramatic. So if it is a centimeter per year, so the 360 degrees corresponds with 210 meters. So then 2.1 meter corresponds with 3.6 degrees. So 1 meter is 1.8 degrees. Well, so you can imagine, right? So basically motion, the changes of the DM, no way, you are not sensitive to that at all. Right? Then you could look at the precision. So suppose that we have a sigma of 1 meter. And so SOTM may have a sigma of, I don't know, maybe 10 meters or so. So if we have 10 meters, so then we have 210 meters is the height ambiguity. So 21 is 1/10 of that. So this is 1/20th of a cycle. So that is 360 degrees divided by 20. So that is 18 degrees. Right. So if we are 1 meter wrong or 10 meter wrong in the SRTM, that would cause a phase error of 18 degrees. Right. So 18 degrees would be 1/20th of a cycle. So it's also 1/20th of 28 millimeters. So that is 2.8 millimeters, is 1.4 millimeters. So we would make an error of 1.4 millimeters if we have a 10 meter error in the DEM. Right, so this already, I told you the sensitivity to deformation is 1,000 times better than for topography. So basically, SRTM is good enough, right? If we have laser scanning DEM for Latvia, great, we'll use it. But when I did this processing or asked somebody to do this for me for Latvia, we didn't have an elevation model, so we just use SRTM. And so we get, if there are errors, it would be something like this, if there's a 10 meter error, right? And I don't think there's a 10 meter error in SRTM. Yep. You had another question? Yep.
Do you have to do some kind of temperature normalization?
Temperature normalization.
Like the buildings expand?
Oh, yeah. We will see that. We'll get back to that. I'm going to show you in the infrastructure from Riga, for example, the bridges, that actually the temperature is visible in the data set. But the question is, do we take compensators? So it's an option. We can do that. So basically, we have in the jargon we talk about 3 main baselines. One is the perpendicular baseline. I showed you, depending, it scales with elevation. The other is what we call the temporal baseline. That's time, right? Longer time, more deformation. And the third one is the thermal baseline. So that is indeed temperature. So if we have time temperature records over time, then we can simply insert that in the data processing, and we can see for each object, okay, so what is the scaling parameter with temperature? And that always makes the time series much better. But sometimes you don't have it, or you don't have time to dig it up from somewhere, and then so in the data set that is online now, that you guys will work with, we didn't take it into account. So that means the temperature is still in there, temperature effects.
Another question, this Riga site, so everything is relative to the topography map when it was taken. All the change, displacement in the study you did is relative to the map, orthographic map done by...
You mean the positioning of the points on the map?
Yeah, because I understood you took the baseline as this orthographic map.
Ah, yeah.
So any change is relative to the date when this map was taken.
Yeah. Just to be exact, so what we do for the positioning is that we use the ellipsoid. So that is not a geoid. We could also, geoid is known, right? But we use the ellipsoid here. And that means that we get geocentric coordinates. And that is not the same as leveling coordinates, because these are orthonormal values that are depending on gravity differences. So this is purely geometric. That's the first part of my answer. The second part is that indeed everything we're measuring is relative inside such a data set. So there is a reference point and there is a reference epoch. Right? So the reference epoch is just the image that we start with or that we choose to be the center of our data processing. Could also be the latest. But we need to make a choice. So where in time do we start? And the reference point is the point of which we assume that the elevation is known and the displacement is either also known or zero. Right? So that means that I think that is maybe why you asked the question, that if you make an error there, it will affect all the points. So basically on the map, if you would ask what you see on this map is displacement rate in millimeter per year. Now there is more greenish, you can zoom in later by yourself, but we don't know perfectly where 0 millimeter per year is. What we do know is how it the relative motion. So if a point is red and the next point is green, then the difference between these two, that is very accurate. But we cannot really say without any calibration where 0 millimeter per year is. Yeah? Other questions? Okay, good. Maybe it is good to, because I don't want to talk too much, so why don't you just go and have a look yourself? So what I would recommend, the best thing is to do is to go to this website. There all the information is. So it's called sites.google.com /view/isa-riga. sites.google.com /view/ESA-Riga. So that is where I prepared, like say, a practical. So maybe before you go on, let me just briefly explain what my intention is. Just 1 minute. So we created this portal. Okay, let's one step back. So if you do, when we did this, Francesco and I, when we did these courses a long time ago, we started basically with making an interferogram, right? You had SAR image 1, SAR image 2, and so ESA has made great software called Snap, and you can use that to make the interferogram, and then you get the fringes, and you can choose images of an earthquake or maybe of Latvia, and you can do that. The problem with that is that it costs time because it's a huge amount of Sentinel are very big images, and so you need to go through processing software. And so, in my opinion, now we are already much further because we don't work with 2 images, but here we work with 133 images. And it's simply a waste of your time to do this here behind your computer. Right? If you want to do it, there's software available. You can find it. There are manuals on the internet. So instead what I wanted you to do is to look and try to interpret the final result, right? So what can we do if we do all of this data processing, which I think at the SkyGeo services it also cost maybe a day or so to process the whole thing. But then you get a result like this. And what I would like you to do is to interact with the data, interact with that result, and try to figure out, ask questions about it. Now on this website, the Google site, here, I've prepared basically a set of questions which I would like you to answer. So, of course, this is on your own discrecy, but so which satellites were used for the given data set? So you can check that. There's a hint on what you can do. So simply go through these questions, write down the answer for yourself, maybe on a notebook. If you don't want to write it, also fine. But I came up with this list of questions for you to basically exploit and get all the information that is in the data. And of course, you can also look if you're from Riga and you know where your house is, go and have a look. That's also fine. But this is the whole practical set that I had for the afternoon. But maybe it's good if you already start now, then you don't need to listen to me that long. Yeah? I'll walk around and I'll ask for questions. So maybe if you could at least go through the first couple of things. So the first question, so the satellite data set, what do we know about the data set over here, and maybe the viewing geometry. Then you already have a bit of an overview. Everything that is related to the satellite. So the first question, which satellites were used? Well, you can see that it's Sentinel-1, right? Actually, Sentinel-1 is a mission. It has 2 satellites, Sentinel-1A and 1B. And if you look at the colored, the dots in the lower part of the browser, you will also see that sometimes they were both acquired. So here, if you zoom in maybe a little bit further, let's zoom in here. Okay, so here they were acquired every 6 days. So this was Sentinel-1A and 1B, and here one of the two dropped out. And then, as some of you may know, Sentinel-1B had a problem, so it's not active anymore. So since December 2021, something like that here, images are out. So here we only have Sentinel-1A and not 1B anymore. Okay, so that is the question on the satellites. Now the spatial resolution of the sensor, that is something that is in the browser. If you click on these 3 dots that I was talking about, you can get that information, the spatial resolution and spatial area extent. Let me show you that here. So the 3 dots here are these two, get layer information. Okay, so now we know that we have the Sentinel-1 mission. It's an ascending orbit. Did somebody explain ascending and descending orbits in the earlier part of the week? No? Okay, well, this is important. So if this is the Earth, right, and the Earth is rotating, this lamp is the sun, so it's rotating like this. So the satellites are flying around the poles, right? Why are they flying around the poles? Why not like this? Huh? It's sun synchronous, but why? 2 reasons. Yeah, so that's a consequence actually. You're flying around the poles because then you can see the entire Earth, right? If you would fly in this plane, you would only see the equator. If you fly like this, the Earth would rotate beneath and you would cover the entire Earth. So every place on Earth you have a measurement. So that's convenient. The other reason that you have that orbit is that it's a stable orbit. You can maintain it for a long time. And you can design it in such a way that if that is the sun, that if you're flying in this plane, the solar panels will always get solar illumination. A radar is a very powerful instrument, needs a lot of power. So you need the solar panels maximally, so it will always be a little bit in an eclipse, but you want to have maximum solar power. Then if you design it in such a way, you can also design the orbit in such a way that, let's say every 12 days, you're really the Earth has made an integer number of revolutions, and the satellite has made an integer number of revolutions around the Earth. So you're really exactly at the same spot. So, question to you guys: how long does one cycle around the Earth take for the satellite? You guys? Interesting, huh? It's about 1.5 hours, close to 100 minutes, right? So the time that we have been talking here, since the satellite has already went around the Earth already more than once, right? So it's very quick. Now, okay, if this is the North Pole, this is the South Pole. If the satellite is flying from the south to the north, we call that the ascending orbit, right? If it is flying from the south to from the north to the south, we call that the descending orbit, right? Now, if this is Latvia, then I may see Latvia one time if I'm flying with the satellite here, so from an ascending orbit. Then we make lateral every 100 minutes around, the Earth rotates, and sometime later I will see it from the descending orbit. So what does it mean for this building? That if that's the north, I don't know where the north is, but suppose that the north is over there, that means that there is east, so where's north? There is north, thank you. There's north, so that means that the descending orbit will come from that direction. We'll see that side of the building. The ascending orbit will go from this direction and look at this side of the building, right? Maybe, I'm not sure if you guys went through this viewing geometry thing here, so I put this KML file here. Did anybody download that already? Yes. Yeah, so that what you should see here is, I think, I hope I have that over here. Okay. Yeah, this is good. So this is where the satellites are for Riga, right? Can you see this? Yeah. Right, so if we zoom in here, this is where we are. It's a bit difficult to see, I think, with the browser, but there's a plane over here. So the red lines are the lines towards the satellite. So I didn't know exactly where we were, so I just picked a point here in the center somewhere. So if we look at the ascending orbit or the descending orbit, we're looking at this point in sky, and the other one is the descending orbit. Let's zoom out again. This is where the satellites are. Right? So we're looking at the area of interest from two different angles. And ascending and descending mean that we're seeing different things. We cannot compare images from an ascending orbit and a descending orbit. And what I did here is I only processed one of the, because it's time consuming, so there are actually, I think, 4 images over here, 4 acquisitions from 2 ascending and 2 descending orbits. And I just processed one. So actually the data that you're looking at were acquired when the satellite was in the ascending orbit. So the satellite was here flying somewhere above Poland, right? From to Poland towards Sweden in the northward bound. And it's looking to the right, and that is from that angle, it is looking at Riga. The other thing that is interesting to see is that, so the time of day, I think that's also one of the questions. Let's see, I think I put that even there. Yeah, at what time of the day were these data acquired, right? And you can see that from the portal. Because, yeah. So the acquisition period was from the 3rd of June 2019 up until the 5th of June 2022. So this couple of weeks ago, this is quite recent. And what you see here, this is the date of the acquisition, at the time of the acquisition, so 1604 and 29.8 seconds. So this is 1603, 29.2 seconds. So there are a little bit of difference, but basically this is basically sun synchronous every time at the same time of day. And this is in UTC, right? So here I think we are 3 hours with summer time further, right? So that means that the acquisitions are at 1904, at 7 o'clock in the evening. That has an impact. So the descending orbits are in the morning. At I think here they would be maybe at 7 o'clock in the morning. The main difference between morning and afternoon acquisitions is that the problems that we have with the atmosphere are different. So in the morning, we are coming from the night. In the night, the atmosphere is quiet. There is no sun, so it's very quiet. Then during the day, what we see now, the sun is warming up the surface. There will be convection. There is turbulent mixing of water vapor. And that means that the ascending images are usually a little bit worse in terms of the atmospheric disturbance. Okay, what else do we see? So it's ascending image. We see the incidence angle. That is the angle with which we look at the surface, basically as seen from the ground. So this angle down over here. So the 31 degrees is the incidence angle here measured from the north, right? Measured from the zenith. So that is also important. So if the north, where was it? North there, right? There, north. So ascending orbit would be looking from the west, from that side. So the incidence angle is quite steep here. So 30 degrees, 31 degrees means that we're, for an urban area, you're really looking into the in between the buildings. What else? The resolution. So this is the resolution of the sensor. I got some questions from some of you here. So 13 meters by 3.7 meters. This is actually range resolution. This is the range direction, and this is the this is azimuth direction. This is range. So basic message is that the pixels that we get on the ground are not squares. They are rectangles, like this classroom is a rectangle. So and one of the questions which is actually quite important here is that So the term resolution for radar doesn't always mean that much, right? So if you talk to people, if people are having discussions with you about, okay, so you've been at that radar course, and is it useful? What is the resolution? They usually have in their mind that optical images. That's what our brain is used to. So if we say we have 25-meter resolution, that's great. I can see a car, right? But for a radar, it doesn't work like that, because my basic example is if you have, let's say, an asphalt parking lot, a flat road, or the runway of an airport, right? That would be very flat. Suppose that I put one lamppost on that runway. It's not so good for the aircraft, but let's do it. Then what we would get is the reflection from that lamppost, right? So the resolution is still, what is this? 4 by times 14, so that is 60 to 80 square meters. But the actual thing that I'm measuring there is just the size of a lamppost, right? So the whole concept of resolution, we should not look at that from the optical point of view, but really from a radar point of view. So if I have a potato field where there's not one single strong object in there, then I probably get the average of that whole potato field. And then there will still be some arbitrary point that I will get. I will measure a position, but where that position is in the resolution cell, I don't really know. Okay, the time, I already discussed that. There are 133 acquisitions, all the little dots that you see over here. So 132 images were used. And the number of points that we have here is 1.9 million. So 2 million points in this data set. So basically, if you talk about the number of observations, it's 2 million times 100, so that is 200, so maybe 300 million observations in this data set, right? Because if you click on a point, you also have the epochs. Then the reference date. So here, the choice for the reference date, we need to say, okay, where is 0? It was set here to the 3rd of June, which is actually the first image. And this is arbitrary. You can decide, where you've set 0 just shifts the whole graphs a little bit up or down. But basically this says that, okay, everything was measured relative to the first image. Now the last one, this is an important one, because the last one says estimated models. And in my introduction, in my first little block, I was talking about the measurements versus the parameters, versus the unknowns. So the measurements are the phases and the complex radar reflections. But I'm not interested in them necessarily. I'm interested in getting a rate or an acceleration, or I always like to translate my measurements to unknown parameters, right? So my example to my students is always if my unknown is the length of the table, right? So that is, okay, I can discuss that, the length of this table, that is what I would like to know. Now I can measure that 100 times, and I can give you the 100 numbers. That's fine, you can make a histogram, you can do nice things, but basically what I prefer is what is the length of the table, right? So that means that you average probably, and you get a sigma for that. So that is the unknown. So the measurements are not the same as the unknowns. So what we did here, because we simply processed the data without knowing what the application was, so we just made some choices, right? In normal cases, you would always sit together with who has a problem, what do you want to solve, are you interested in the bridge, are you interested in the peat soils, are you interested in the railway, whatever, then you would change your way of processing. Because we didn't know, we took a very arbitrary approach. So that means that we took 3 models combined, so a linear model, it means constant rate, then a quadratic model, it means that if a point accelerates slightly, then we can accommodate that with a quadratic term, and a seasonal component. And this is your question about the temperatures. We have seasons, we know that things expand in the summer, go down in winter, and actually if you look at soils, it's the other way around. So for example, an electricity mass of metal will go up in the summer, so it will get closer to the satellite, but a peat soil will dry out in the summer, so it will go down, so it will be further away from the satellite. So if you look at that as a sinusoid, the maximum and minima will be shifted, depending on which point you're looking at. But this means that we are using these parameters, so these are basically like 4 or 5 parameters, plus the elevation as the unknowns in our data set. Yeah? I think that were most of the first questions that I put here. So spatial resolution, spatial extent, temporal resolution, the heading of the satellite. We didn't discuss that. We can get to that later. Time of day and how many acquisitions. Yeah, this was the first little block, right? So, and again, so if you're interacting, you know, you can click on a point and zoom out and zoom in and click on another point. At some point you get bored, right? So my advice is to go through these questions, try to answer them for yourself, right? I will discuss some of them, and probably not all. Okay, then the thing, I think we have another 15 minutes left, right, before the lunch break.
Actually not, but maybe we are flexible.
Oh, the lunch break is at 12, right? Yeah.
Normally the
Okay.
lunch break is at 12.
Okay. So I can also do this after lunch. Are you hungry? Would you guys? Or shall I just do this little part? So I want to talk about the precision. Maybe I'll just do it. It's a little Python script that I would like to show you. And I think it's this one. I made this little script to get a feeling for the precision of the observations. And I'll not go through all the details, but basically the important number that I will start with here is what we call the signal to clutter ratio. Okay, what is a signal to clutter ratio? If I have a certain field, let's say, and in this field there is a reflector, like a big thing which is reflecting the signal back to the radar. But the field is for maybe a potato field, so I have all kinds of reflections over here coming from the rest of the field. So what I will measure then in the complex domain is this very strong amplitude from the reflector and all kinds of little reflections from the ground. So these will always be very little vectors, many different directions. Now this is what we call the clutter. This is a radar term, so how much signals am I getting back that do not make any sense, that are not interesting? And this is the signal. So the signal to clutter ratio is the signal divided by the clutter. Now, if we usually express it in dB, so if that number is big, I have a very high signal, very strong signal, and a very low clutter, very low noise. If that number is small, I have very big, relatively a lot of noise. Now that is what I try to do over here. So I'm going to show you now what happens if I have a high signal to clutter ratio. That's what you see over here. Let me explain this figure to you. So this is the complex domain, right? The complex numbers. So I have the real part over here and the imaginary axis over here. This is the center, and what I'm simulating here is one scatter, like one reflector which is very strong, and maybe 1,000 elements of clutter. So then I can say that the amount of clutter, the amount of noise is very, very small. You see that over here in this bunch of little blue points. That is basically the noise. The signal amplitude, I always set that to 1. So that is this vector, and the angle is random. I put it to 30 degrees over here. So this would be a case which is very good, right? Because I have a very strong signal and very little noise. Now let's see what happens if we increase the noise, and it would be equivalent to, so let's say put it to 10 dBs. Here. What do we get then? We get this. Okay, so now the length of this vector is still 1, the angle is still 30 degrees, but now you see that the noise is much bigger. Now the main message, so in the real axis, it's this Gaussian distribution, so these points, and the imaginary axis also a Gaussian distribution. We call this circular Gaussian. That's the type of noise that we have. Now, what you get from this point is that if this is the noise, then this red vector the phase is much less clear. Do you understand that? So if my arm is this red vector and I have so much noise around it, it could very well vary in this direction. In the previous one, where the clutter was only around this, my variation of the phase is very limited. Right? If I go even lower, so this is the blue circle that you see over here. So if I go even lower, let's go to a signal to clutter ratio of 1. That would be very bad. The noise is equally big as the clutter. Then we get this. So now this is the signal, this is the clutter. It's the distribution, the noise is very, very big. So now this angle, the quality with which I can measure the angle, so the phase, is very, very bad. Actually here it is, the variance of it is 61 radians, 61 degrees. Now why is this important? So what I would like to show you with this example is that basically every pixel, if you have a radar image, billions of pixels, every pixel has this kind of situation, right? If I have a cornfield, for example, or a forest, and there is something in the forest that I'm interested in, then the forest had a lot of noise. So that means that for that particular pixel, the quality is much poorer than, for example, a pixel which is a corner reflector on the runway of an airfield, right? The runway of an airfield is asphalt, is flat. I'm looking at that from the side with the radar, so most of the signal goes in, bounces away into space, and I get almost nothing back. That's very good, because if I put something there, then the noise level is very, very low. So the main message is this quality is not something that is only dependent on INSAR or the satellite or so. It is dependent largely on what is happening on the ground. And I remember, maybe you were there, Francesco, we had some of these first meetings at ESA when the INSAR thing came up, and we had, I think maybe it was a fringe meeting, and there was this Irish manager from ESRIN. Yeah, Doherty, yeah. He, at some point, he was a little bit annoyed because we were always saying, okay, you know, we don't know really exactly how good is it. And he asked, just give me the sigma, right? Don't make such a big academic story, just give me the sigma. How precise is this, right? And at that point, he wasn't so well in trying to give that answer because it's a valid question, right? But it's a question that you cannot answer because every single pixel has a different sigma. It depends on what is there on the ground, right? So you can talk about the precision of the sensor, then we get up to about 23 dBs, I think. That is what we would enter here. So if we have perfect data, I think for Sentinel it's 23 dBs. So what is the level that we can get then? That is this kind of situation. So the sigma of the phase is 4 degrees. And this is what gives us the sub-millimeter precision. So the sensor is able to do that. But every measurement that we get is the combination of the sensor and a particular area on the ground. And that is always different, right? And it changes over time. So it is impossible to answer the question, just give me the sigma. How good is INSAR? How good is INSAR if you compare it with leveling? That's a silly question, right? Because with leveling, we always know what we're measuring. We can touch it with our finger. But with INSAR, it depends what we want to see. If we want to see only the best points, it's okay. I just filter out the best points. You have a slider on your portal. You just slide that quality level to the right, and you get less points, but they will be much better, right? If you want to have more points, you slide that thing to the left, and you get more points, but there will be also more noisy point. So you cannot say INSAR is better than leveling or the other way around, or how does it compare to GPS, because we're not comparing the same things. GPS receivers are always the same thing. You can say something about it independent where you say it, where you put it, roughly speaking. With INSAR, every square meter is different. So basically we have to learn to deal with that. And we have to learn that, okay, some places we get good data, other places we get a little bit worse data, and depending on our applications, we make a choice. Yeah? Maybe this is a good point to stop, have lunch break. Yeah, if you have questions during lunch, let me know, and otherwise we'll move on here.
Normally there's 1.5 hours break for lunch.
Yeah.